covered uh, groups and rings. So remember that groups have four assumptions. We say G0 to G4. So G0 is closure, and G1 is associativity, G2 is identity, G4 is inverse. These four requirements were considered by mathematicians the most fundamental assumptions according to 100 years of experience of studying. And there's another one, that's G5, that's commutativity. So if G5 holds, then it's a it's an abelian group. So we have some examples. Okay, and then okay. And we also talked about greatest common divisor, GCD, aka HCF. And there's an algorithm called Euclid's algorithm to do that, to calculate the greatest common divisor of towards two numbers. So here's one example. We have seen that last time. Now let's move on to groups. Okay, so groups we know. G0, G1, G2, and then rings. So the requirements of rings, using the language of groups, is easier to formulate. So the ring with addition alone forms an abelian group. With multiplication alone, it forms a semi-group. Okay. In addition to that, we have distributivity. So that's a ring. Now we have seen an example, Z6. Let's take a look at Z6. The number of elements are 0 to 5, 6 elements. And the two operations defined. The addition is defined mod 6. So it's ordinary addition with an extra mod 6 operation. So that's addition. Multiplication is done in the similar fashion. Ordinary integer multiplication followed by a mod operation, mod 6 operation. Oh, okay. So yeah. Sometimes I have this Windows problem. Yeah. I don't know what happened, but sometimes it occurred. Yeah, so let's go to rings. Sometimes I press the button too quickly and then it will break. Okay, so that's rings. Okay, let's move on to fields. So fields. A field is a ring with some extra properties. So it's a even better mathematical structure. So it's a ring. In addition to that, it's a commutative division ring. So in other words, in such ring, multiplication alone, if we remove 0, then it forms an abelian group. So then we can have all four operations defined: addition, subtraction, multiplication, and division, with the exception that you cannot divide by 0. That's a field. Okay. So the fields is the basic idea of fields. We have a template for field. The basic template is a set of real numbers. Okay. The basic template for rings is a set of integers. Okay. So in the set of integers, you can define addition, subtraction, multiplication, but not division. Okay. Sometimes you may have division, but most likely, okay, for example, you can't divide 3 by 2. Okay. But sometimes, for example, you can divide 6 by 2 or something. So you cannot guarantee the existence of the division operation. But in fields, you can can pretty much divide everything, except we cannot divide by 0. So that's the only exception. There are there's very limited number of fields, very limited types, because such requirements are very strong. So what are the fields we have? Let me explain. So the basic template is the set of real numbers. Okay. And then we also have the set of complex numbers. That's also a field. And we also have the set of rational numbers. Okay, rational numbers, the formal definition is this. If every element in this, every rational number can be represented as a factor of 2 integers, okay, such that q is not 0. Okay, so q can't be 0. So this is the set of rational numbers. These are the three basic types of fields. In addition to that, there's another category. That's the thing we're going to teach. That's our main topic, the finite fields. These three types of fields are infinite. There are infinitely many elements in these fields, in each of them. So although these fields provide good property, the only problem with these fields is that we cannot use limited memory to represent their elements. Okay. Actually, we can't even represent the set of integer using finite memory, because the integer can grow arbitrarily large. Okay, so we can't even represent z, let alone real number, complex number, okay, and these fields. So actually, there are very limited types of fields. In addition to these three, there's another one called finite field. That's our main topic. If you ask me, are there any other types of fields? Actually, there are, yeah, but they are not of our interests. So we omit those. There are other fields, just to let you guys know. There's algebraic number field. There's function fields. Okay. There are many other infinite fields as well. Okay. We won't cover those things. Okay. An example, finite field. Let me give you the first example. Okay. So let's take a look at this. Okay. 0, 1, 2, 3, 4, 5 elements. Okay. Including 0. And then we have addition and multiplication. Okay, defined. This is okay. And then we have subtraction as well. We can always subtract anything from another. That's okay. The only problem is division. Do we have division? Can we define division? Let's verify. So the easiest way, without any mathematical tools, the dumbest way to do that is to list a multiplication table. Yeah. So let's do that, and then we'll see whether it's a field or not. Okay. So let's. Oh, by the way, before we're doing that, okay, we look at this 0, 1, 2, 3, and then multiply operation. Obviously, addition alone forms an abelian group. This is okay. So the only problem, and then also distributivity works just fine because it's a ring. So we have, the only thing we have to verify is that whether or not it's an abelian group. Okay, so in which there are five assumptions. So G0 and G0, G1, G2, G3, G4, in which everything is okay except for G4, G3. So the only thing we have to verify is that whether or not there's an inverse element. Everything else is okay. Because, for example, like distributivity, they hold trivially. But the only thing is we are not sure whether we can have an inverse element for each element except for 0. So let's take a look at this, and then we let's do the multiplication table. We don't have to list 0 because we don't have to worry whether or not 0 has an element. 0 has an inverse element because 0 is not considered in the in that case. So if you multiply by 1, that is okay. Multiply by 2. 2 times 2 is 4. 2 times 3. 2 times 3 is 6. Mod 5. Right? Mod 5 is 1. So in other words, 2 and 3, they are inverse of each other. So they're inverse of each other. Okay. And then, okay, 3 and then 2 times 4 is 3. Okay. And then we have 3. 3 times 2 is 1. So 3 times 3 is 9. 4. 3 times 4 is 2. Okay. And then we have 4. So this is 4. This is 4 times 2, 3. Okay. So 4 times 2 is 1. So what we can deduct from the multiplication table is that 1 and 4, they are both inverse of themselves. And then 2 and 3 are inverse of each other. So indeed, everybody has an inverse, a multiplicative inverse. So this is a field. Okay. So this is actually a finite field. It's a field, and we only have 5 elements, which is finite. So this is a finite field. This is one of the easiest finite fields. You guys can verify that this is not a finite field because some elements do not have inverse. So when you have mod 4, you have a problem. You guys may ask, why mod 5 is okay, but mod 4 is not? Why? Actually, that's because mod 5 is prime, but 4 is not prime. 4 can be the number 4 can be factorized as 2 times 2. So if it's not prime, and you mod that number, it's not a field. Yeah. If it's the converse is true. So if it is a prime, then when you do similar things, mod that number, then it's a field. So let's talk about this. So this is called the Galois, also known as the Galois field, because it's first introduced by the French mathematician and called Évariste Galois. It's not pronounced Galois. It's pronounced Galois because it's French. And this guy is one of the most genius mathematicians ever. Actually, in my mind, there are only, in my humble opinion, I only think there are 3 really, super mathematicians in the world. Yeah. Galois is one of them. Yeah, like the most genius guy. Okay, so this guy, Évariste Galois. He was born during the French Revolution, and he is so talented that he was reading, research papers written by the big names in the same era when he was when he was a teenager, and he what happened to him it's a tragedy because he died so young. He died when he was 22 years old. 22. So unbelievable. And then what's worse was he actually spent the last 2 years of his life in prison because he was politically very active. He has a strong political ideas. So then that time was a really turbulent era. So if you guys know, there's a guy called Robespierre, which is a very famous. It's that period is really turbulent. And then there's this guy, Robespierre. He's famous for the way of execution called guillotine. So this guy pretty much executed all his political opponents using guillotine. So a lot of people were killed. And finally, he was executed by the guillotine himself. So, and then Galois, this guy, Evariste Galois, when he was 22 years old, he knows that, he developed these theory, this big theory, and then he, I think he and one of his opponents fell in love with a lady, and then he was a really good mathematician, but he's not good at using pistol. So finally, he went to a duel, and he got killed at the age 22. Then before the famous duel, he actually thought, oh, he may die, so he wrote all this stuff, and then sent them to the one of the most important, I would say, big name in the area of mathematics. That's the, what is it called? The Institute of Higher Studies in France. It's kind of like 有点像我们中研院长这个时候，法国有一个这个，等于说是最大的大头。那个时候他知道他自己快死了，因为他去决斗。可怜的是这个数学家，他虽然很会算数学，可是决斗不是很厉害，最后被人家一枪打死了。So he actually sent to the that big name, and then that guy was at that moment, the Institution of General Studies was, I think, Fourier. But what happened was, after Fourier received his research papers, he died immediately. So then the next one is Cauchy. And then Cauchy couldn't understand. And then they just put it there after 50 years. Finally, finally his successor understood and then published the results. 其实这个 Galois 他当时他其实就是寄给就是先寄给那个嘛傅立叶嘛，那傅立叶就很倒霉，收到没多久死了，下一个柯西，结果柯西不是很相信他啦，然后柯西就想说你这家伙才20岁，就20岁的人能懂什么东西啊？就放在那，而且他也觉得写的乱乱的，看不太懂。所以当时他并不是用这种语言写的，所以很难懂。就一放50年，就最后有一个人把它看懂。So actually, 50 years later, there's a guy who finally understood. What is that? What's this? Liouville. You've got very complex analysis. There's a Liouville theorem. So he actually realized. And the only contribution I would say of Liouville is that he understood Galois' idea and published those. So 大家父辈有没有学过这个 Liouville 定理？有听过的名字吗？这个人一生最大的成就就把Galois东西看懂了。办大学说这人才22岁就死，他记的时候大概是19岁。然后那些，你想想看，一个中研院院长收到一个19岁的一个小毛头的这个的论文，然后写的又有点乱，字迹很潦草，什么东西就丢在那里看也看不懂，一放50年。Okay, so anyway, this is Galois field. It plays a key role in cryptography and many other applications as well. For example, error correcting code. So the number of the elements in the finite field is finite. In addition to that, there's a big theorem. The number of elements must be the power of some prime. It's really big. So in other words, let's take a look at this finite field. For example, we can have a finite field of 2 elements, and then 3 elements, 4 elements, and 5 elements. They're fine. Okay. And then 7 elements, and 8, and then 9. Okay, they're fine. But there's no GF6. 没有 GF6， 为什么？6不能写成质数的平方。好，这2、3、4、5都质数没问题。对不起，2、3、5、7是质数没问题。4跟8 一个二次方，一个三次方，93二次方刚好都可以。10以下只有6不行。And then we use a GF something to denote this type of field. So GF p to the power of n. Okay? But we're not interested in all types of finite fields like this. We're only interested in 2 types. There's one called GFP, which is a prime. Actually, we have just seen one of those. The field we saw earlier. 0, 1, 2, 3, 4. This is the field of 5 elements, and it's also the field derived from Z5. The Z5 is a ring. If you use the ring language. In addition to that, it's a field. So if we regard it as a field, actually they're the same thing. We use this term GF5 to represent that. And computer scientists generally prefer this language, but mathematicians generally they prefer this language, F5. So if you see anybody writes F5 with a double stroke for F, this is written by a mathematician. This is written by a computer scientist. So G5 is the field. That's GFP. So G2, G3, GF3, and GF5, GF7, okay, those are GFP. We have a special name for that. This is called a prime. They are called prime fields because P is prime. And there's another type called GF2 to the power of n, okay, because 2 is prime. Nobody's interested in GF3 to the power of something. Nobody's interested in that. Because everything in the area of computer science is binary. So GF2 to the power of something also plays an important role. So GF2 to the power of n, we have another special name for that. They are called binary fields. So for example, like there are many binary fields used in cryptography, in lots of stuff. For example, in AES, we will be using GF 256, which is 2 to the power of 8. And in, for example, like satellite communication, sometimes they use GF 1024, 2048, even 8096, GF 8096. So those fields are used. And in lots of other error-corrected codes like LDPC, sometimes they use even larger binary fields. Okay. Let's take a look at GFP. So this is called prime field, and then if we regard them as rings, they're written as ZP. Okay, so their definition is very straightforward. So we have P elements. So to name those P elements, we generally include 0 because 0 is necessary. We have to have an additive eigenvalue. So 0. So we go from 0 to P minus 1. So altogether we have P elements, and then two arithmetic operations are defined. So we have addition mod P and also multiplication mod P. So the important thing is we have to show that it's every element has a multiplicative inverse, just like we verified GF5. You know, all other requirements are trivial, but the existence of multiplicative inverse is not trivial. But we will cover that because this can be done. This can be calculated using extended Euclidean algorithm. We will have a special. This is a special topic. We'll talk about that later. So they form the finite field GFP. The thing is, we have to verify this later. Every element except for 0 has a multiplicative inverse. Okay? So if that happens, then division can be thought of as multiplication with Actually, it just happened last hour. 怎么办呢？这个怎么办呢？Oh, okay, great. 啊，有点夸张。刚 Okay. So I think it's okay. Let me see. Okay. Oh. Oh. 哎，它没有吗？对。关再开。哇。关再开。好，这个要一阵子。哎呀。有亮吗？好像没亮啊。哎呀，好像。Let me pause this. Yeah, pause. Okay. So every element other than 0 has a multiplicative inverse. That is, we call the division is well behaved because we can perform all 4 operations, addition, subtraction, multiplication, division in GFP. Okay. If this P is not prime, then it's not a field. It's a commutative ring with unit, with 1. Okay. Generally speaking, when we use this letter P, we pretty much assume that it's prime. And if we want to use an integer which is not prime, we use m or n. Okay, that's what mathematicians do. So P usually we assume that it's prime. Let's take a look at the multiplication table of GF7. So this is GF7. We can check that. We know that 7 is prime. For each row, if you find an element which has the entry 1, that means it has a multiplicative inverse. So indeed, we can find each row there is 1 here. So in 1 here, that means 1 times 1 is 1. So we do have inverse for each row. Okay. If there's some row that you cannot find any 1 on a row, then it's not a field. Okay. So in this case, every row there's a 1. This is the element 1 exists somewhere. So multiplication table tells us. And this is the inverse table. So as we can see that 1 and 6, they are multiplicative inverse of themselves. And then 3 and 5 are multiplicative inverse of each other. 2 and 4 are multiplicative inverse of each other. Okay. Let's take a look at the algorithm. This is a really important algorithm called extended Euclidean algorithm. Let me show you. Finding the multiplicative inverse in ZP. So if this can be done, that means every element has an inverse. First, what we do here is we apply Euclidean algorithm or Euclid's algorithm. So here's an example. So we find the multiplicative inverse of 337 in Z1021. So what we do here is we first we do Euclid's algorithm to find its GCP. So we divide 1021 by 337. Okay. And then we find that we have the quotient is 3, and then the remainder is 10. Okay, and then we keep going. Okay, in the next iteration, we divide 337 by 10. So keep doing, and then finally the result will be 1 if they're relatively prime. So in this case, finally what we get is their GCD is 1, which is which is obvious because they are relatively prime. Okay. So if two elements are relatively prime, you will always end up with 1. Because if two numbers are relatively prime, that means they don't have any non-trivial greatest common divisor. Now, in this case, 1021 is prime. So a prime number must be relatively prime with any number except for its multiples. Okay? 所有的质数它一定跟其他的数都互质，但它自己的倍数不行的啊，你 p 不能跟2p 或3p 互质，这是不行。但它跟其他的都会互质，所以你只要是质数最终，你就会得到 b。So this is called the Euclid's algorithm. Now there's a second half of this algorithm. It's the extended version. They're called extended Euclidean algorithm. We use some mathematical tricks called backward substitution. Let's take a look. So what we do here is we start from the last line. And then we go backwards. So first we move this term to the right. 所以从最下面开始，然后我们把这符号移到右边去，然后我们从1开始倒回来看。你看好。对不起，我讲错了。这个不把它移到右边，我们从从1这尾巴看回去，1等于7减掉2乘3，从这样看。So let's go backwards. So what we do here is we look at it backwards. So 1 is represented as 1 times 7 plus minus 2 times 3. So using the language of linear algebra, we kind of have a similar idea as we represent 1 as a linear combination of 7 and 3. That's pretty much what. 我们把这个看成线性组合啦，那这个1跟负2是系数，所以1把它表示成7跟3的线性组合。那接下来我们要一直迭代回去。那 So the idea is using the last iteration, we can represent 1 as a linear combination of 7 and 3. And then 3 can be represented as a linear combination of 10 and 7. So then if we combine those, then 1 we obtain, which we obtained in the last iteration, can be represented as a linear combination of 10 and 7. And then if we go backwards. Finally, the goal is to represent 1 as the linear combination of 1021 and 337. That's our goal. So let's do that. So we do this. 7 and 3. Now, using the using the formula that's bottom to the that's next to the bottom formula, we know that 3 can be represented as 10 plus 10 plus minus 1 times 7. So then we have 2 multiples of 7. So here we have a multiple of minus 1, okay? But this minus 1 is going to be multiplied by minus 2, okay? And then here we have another copy of 7. So if we group those, altogether we have 3 copies. 这个7有一份，这个7有负1份，但是负1再乘负2，所以总共负1乘负2就是2份。这边有2份的7，这里有1份的7，加在一起就3份的7。哎，那这个10的话呢，就负2就搬过去这样子，然后我们继续这样子一直做，好，最终表示成呢，这个1021跟337的线性组合。So finally, we'll represent this 1 as a linear combination of 1021 and 337. And these two parameters are extremely important because that's actually our answer. So finally, we have this. Okay, and then let's take the mod from both sides. Mod 1021. So here we have a multiple of 1021. So here, if we mod 1021, the whole thing disappears. The only remaining thing is 306 times 337. And then on the left, it's 1. So finally what we get is this. So finally, we get (306) times 337 is congruent to 1 mod 1021. This is what we get. This is exactly the definition of multiplicative inverse. So this tells us these two numbers are multiplicative inverse of each other. Okay? That's the way we find multiplicative inverse. So if we can look at these calculations from a more general point of view. Point of view, we can see that as long as we get this 1, okay, then we can do all these things. Actually, even though we the two numbers, the GCD is not 1, we can do the same calculation. But if it's not 1, for example, you do something, for example, 3, and then we do lots of backward substitution, right? If you get your result like this, this is useless. Okay. So the only case which will make these calculations meaningful is that we get this 1. Otherwise, even though we can still do those calculations, they don't make sense. I mean, they're useless. And so this 1 is absolutely necessary. And then we'll only get 1 if these two numbers are relatively prime. Okay. So if P is prime, we can always do this calculation, and then they will always make sense. Because a prime number will always be relatively prime with every other element, except for 0 and then its multiples. Right? That is why it will be let's take a look. That is why every element in GFP will have a multiplicative inverse. Yeah, the reason is obvious. Yeah, it's out of battery. The battery is dead. So, if if P is prime, then it's always guaranteed that P will be relatively prime with every element, every non-zero element. So that actually means it's a field. Okay. Such calculations won't make any sense to in binary fields, in these fields like this one. Okay. For binary fields or general finite fields, such calculations are not enough. We will talk about that later, but I mean for this moment, we can only know that GFP, only prime fields, we can do these calculations. Okay. For general finite fields, or binary fields, special treatments are needed. These calculations alone are not enough. And we'll talk about those calculations later. So it's GF7 and then multiplicative inverse here. Euclid's algorithm. So that's the idea. Any questions? Oh, by the way, these calculations are really important. So let's just make sure that everybody can calculate. By hand we do this. However, you guys will be it will be required to write a program to find the multiplicative inverse. In that case, it won't be this. I will talk about that later. Yeah, I will have a special lecture regarding how to find the multiplicative inverse. So this is hand calculation only. So what we do here is not the same thing as, when we write a program, it's difficult to implement this idea. It's possible, but it's difficult. There is an easier way to do that. And then that way is another way to write to find the multiplicative inverse. There are many other ways to do that. Okay. It's just if you do hand calculations, this is easier. But if you write a program, there are other ways. So they're different. So there's some difference between hand calculation and writing programs. Okay. We'll talk about that later. So some remarks. If n is not prime, then Zn is not field. Because if n is not prime, that means there must be some factors. For example, like take Z6, for example, right? Then 6 is not prime because 6 can be factorized by 2 and 3. These numbers won't be relatively prime with 6. So those calculations cannot be applied. So then they're useless. Okay. So in that case, the inverse may not exist. These numbers, these factors will not have inverse. So under what condition will x inverse exist? But it's easy, yeah. Only when x is relatively prime with n. So that's the idea. Now, let's talk about the general finite field, theory of general finite field. So before that, let's talk about polynomial arithmetic. So polynomial, so this is polynomial. We know that. It's an expression. From a mathematical point of view, a polynomial is just an expression. Okay? This x are called this x is it's kind of like, you can regard it as a variable or something. Okay? But if you guys read any books regarding polynomials, they will never tell you what x is, because it's not necessary. Okay? So the thing is, we can pretty much regard these as a collection of parameters, coefficients, I should say. So in that case, for example, like this fx is, you can regard it as an minus 1, an minus 2, until a0. You can pretty much regard it as a vector. Okay. And a polynomial is actually, a vector space. A vector in a vector space. But they have an additional operation called evaluation. Evaluation in Chinese, which is 代值。所以一个多项式，它其实你可以把它当成就那些系数而已。它系数就多项式，就把它当成向量就好。那所以你多项式可以相加嘛，两个相加你就把它当 vector 相加就好。它没有什么特别的。但它唯一的差别就是说，它多了一个代值的动作。你可以把 x 用某个东西代进去，你就多了这个动作而已。那这个动作呢，它当你不做代值的时候，它就是一个 vector。是这样子，所以我们可以把它想成一个 vector space， 多了一个代值的这个动作，多了一个结构在那。So there's one extra stuff in addition to a vector space. So we can have this evaluation operation, and because of this evaluation, we can perform multiplication. Okay. So both addition and multiplication can be performed on polynomials. So addition can be performed, it's no big deal. We just add those corresponding terms. And then for multiplication, we follow the definition we learned from high school. And then these operations can be performed, and then this actually forms a ring. called polynomial ring. And then we have a special symbol for that. So this R, then if R is a ring, then we have the square bracket X. This is called a polynomial ring. So naturally, polynomial we can extend addition and multiplication operation on a polynomial if we have a ring. So that's the idea. Okay. So this is called polynomial ring. Okay. So in a ring, we have addition and multiplication. Then we can extend this operation on its polynomials. That stuff is called polynomial ring. But we may not have division. Okay, so polynomials, we have addition, subtraction, and multiplication. 3 operations. Okay. And if we have a field, that means we have division in the field. Can we extend the division on its polynomial ring? Sometimes we can, sometimes we can't. Let's take a look at this. Let's take a look at ordinary ZX arithmetic. So Z is a ring, okay? So ordinary arithmetics, we have X and GX. Addition is no big deal. We add them up. Subtraction is no big deal. Multiplication, so multiplication is no big deal either. It's just the number. The degree will grow. So it's not, if we talk about multiplication, then it's not an ordinary vector space anymore because we cannot multiply 2 vectors in a vector space. But in a polynomial ring, we can. So it's kind of like a vector space with some additional multiplication structure. But I mean, 2 vectors, if you regard them as vectors, when you multiply them, because their degrees grow, so they may not lie in the same vector space, right? 所以2个向量乘在一起，如果把它当向量看，乘在一起，它是向量没错，但是它不一定会在里面，因为它的 degree 可能会爆掉。对，那就要看你的原本的向量空间 degree 是不是无穷的。如果 degree 是无穷的，它就不会爆，那就是无穷维的向量空间。这样子可以，你可以，它就有个乘法结构在那里。So this is ordinary arithmetics. And then we can also apply other polynomial, other rings and consider them polynomial. For example, we can use Z and X arithmetic, in which all elements in the coefficients are in a ring, which is not an integer. It's some rings. For example, Zn. Okay. So for example, let me tell you guys an example. So Z2, for example. Okay. So we have, this is a polynomial. This is another polynomial. Okay. But the operations are performed in Z2. So when you perform in Z2, there are only zeros and ones. So the operation is a little different. The addition here in Z2 is actually a finite field, right? Because 2 is prime, Z2. Z2 is a field because Z2 is 2. 2 is prime. So we have addition and multiplication. So addition, there is no big deal, but addition is pretty much like XOR if we use 0 and 1s to represent them. Okay, because if we look at the addition table, right, addition, 0, okay, and 1, if we look at the addition table. If you look at the addition table, addition is actually XOR, right? And then if you look at the multiplication table, multiplication is the end. So we do have 2 operations. This is a very special finite field because this is it's very useful in the world of computers because binary numbers are everywhere. So with 2 operations, XOR and AND operation, it's actually a field. It's not AND and OR. It's AND and XOR. 所以 XOR addition 好，所以最自然的逻辑运算是 AND 跟 XOR， 而不是 OR，OR 反而是一个非线性的一个运算。Let's take a 10-minute break. Now let's take a look at the Z2X arithmetic. This is the polynomial ring. Polynomial ring, a arithmetic. So these coefficients, they're not integers. They're in Z2. So E2, their operations are, you can regard them as binary numbers with two operations, XOR and AND operation. So we can, if you add them, we have one copy of x squared. This is another copy of x squared. So 1 plus 1 is 0, okay? So you add them up, x squared will be canceled with the s squared here on the right. So addition is this, and the multiplication is this. Yeah, maybe. So this calculation is a little different from what we have learned in high school, but these calculations are quite useful in calculating, in many applications. For example, so let me do this calculation. So x cubed plus x2. So this is fx, okay? And then it's I generally like to add two zeros there because this is the linear term. This is constant term. So this multiply by this x to the power of fifth, x to the fifth, x to the fourth, okay, x squared. Yeah. Now we do this multiplication. So we can use this type of multiplication table to do that. For example, so here we have two zeros here. Okay, we add two zeros. Starting from here, okay, x squared times 0, 0. X squared times 0 here. X squared times x squared, which is x to the power of 4. Okay, x to the power of 5. This is x squared. Okay. And how about this? x5. So x squared, we have another zeros here. And then x5. Okay, x5 times x squared. Okay, so this is 0, another 0, and then x to the power 7 plus x to the power of 8. So altogether we have x to the power of 8 plus x to the power of 7 plus x to the power of 5 plus x to the power of 4. Okay? Yeah, something like that. That's multiplication. Oh. So yeah, this shows that I actually did the wrong calculation. I multiplied by the wrong. Yeah, actually this is not this example, but anyway, you guys got the idea of what I was doing. So this is Z2X arithmetic. Now let's take a look at. Now, this is still not enough. The reason is when two polynomials, after they multiply, the problem is the degree grows. Okay, so you cannot have a finite dimensional polynomial set in which multiplication will be closed. The problem is closure, right? The point is to design a mathematical structure such that we can use limited memory to represent those. Okay. That's the point, because these are mathematical structures. They're purely conceptual. The point is we need to kind of simulate the multiplication operation, but the point is we have to represent them using finite memory. So addition is okay, but the problem is multiplication. So multiplication after two polynomials multiply, their degree grows. That's the main problem. So we need to have another way to kind of limit those to polynomials. Now, the trick is to do polynomial mod. So when you mod a polynomial, you will limit the degree to a certain degree, because anything that grows higher than the polynomial, for example, gx, will wrap around. So this is an important trick. So we can actually we mimic the modular operation in integers. We can actually pretty much copy the same thing in the set of polynomials. We can do the long division using polynomials, like what we have learned in high school. These are similar. So these concepts, they can be carried over, from the set of integers to the set of polynomials. So we can have a polynomial. We can have this is called the dividend. This is dividend, the divisor, quotient, and remainder. These concepts can be carried over to the set of polynomials. Okay? So we interpret this Rx as a remainder, and then we can define the congruence in the set of polynomials as well. So we can say two polynomials are congruent to each other, mod another polynomial. Okay, and we can also carry over the concept of division. Some polynomial divides another polynomial. We can pretty much carry over this concept to the polynomial ring. So the set of all polynomials mod a fixed polynomial forms a ring. This has a special name for it. It's called the quotient ring. Yeah? And in math, mathematicians generally write this way, Rx/Gx. But computer scientists prefer Rx mod Gx. Okay, two different languages. Yeah, two different ways to do that. This looks a little abstract, right? But actually, if we look at some concrete examples, they're not abstract at all, and then they're easy to understand. They're just a little different. Let's take a look at the quotient. Okay. Yeah, let's look at some quotient ring example. Okay. So the let's say the ring is F2, okay, or Z2. Okay. We can do this mod stuff because they're similar. For example, like let's take this for example, x cubed plus x plus 1. Okay, let's say gx is equal to x cubed plus x plus 1. Let's fix this polynomial, and then we can do a lot of calculations as well. Whatever polynomials you have, you can mod this one. So we consider, for example, f2x mod is gx. So what does that mean? So for any polynomial, we divide gx and then find the remainder. So whatever polynomials you can do the division, right? And the division is very similar to the division we learned. It's long division. For example, let's say we have this polynomial x4 plus x plus 1. Okay, let's take this for example. We can do a division. So how to do the division? So this is easier to represent, but there's some gap because there's no cube. So actually, it's better to add a 0. It's actually good to add a 0, for better calculation, like this. Okay, and then you can divide this. X cubed plus 0 plus x plus 1. And then you can do the division. So we have x cubed, this is x to the 4th. So the quotient must be x. So then x times this is x 4th. And then we have a 0, and then we have an x squared and then plus x, right? And then this is subtraction. Remember that subtraction and addition in GF2, they are the same. They're both XOR. So in other words, there's no difference between addition and subtraction. They're both XOR. Okay, so the XOR, XOR, XOR. So X4 to XOR, X4, they actually cancel each other. They cancel each other here. And then here, it's X plus 1. This is the remainder. Right, this is the remainder. So we can write it this way. So in other words, x fourth plus x squared plus 1 is, we can say this is congruent to x plus 1 mod gx. So this calculation is pretty much the same as integer calculations. Yeah. And then, well, this calculation is okay. We can further simplify this by writing only ones and zeros, because otherwise it's too error prone. So instead of writing x cubed, we can write this, and then there's no addition. So we actually, it's better to write this. It's better to write this way. So those are not numbers. They actually represent polynomials, right? You guys know. So this is x, it becomes this. Right? So this actually becomes polynomials. And then if you write it this way, it's easier, it's less error prone. Otherwise, sooner or later you mess up with the degrees. It's very easy to make mistakes. So I actually prefer this way. I will write it this way later. 以后都写成01了，这样子比较不会错了，比较不会错。大家确认一点，这不是数字哦，这不是数字，你不能把它当成整数哦。比方说1011，对不对？你把这个当成什么？这个是3再加8是11，你不能把它当11哦，你当时就完蛋了。这个除法是多项式除法，它不是整数除法，它的规则不一样，它的进位规则不一样。你把它当整数会进位，多项式是没有进位的，知道吗？好，所以说不能把它当数字来算，我们只是用数字来表示它而已。Okay. Modular polynomial arithmetic. So we generalize this, right? So the quotient ring. The idea of this quotient ring is you mod something, right? Mod something. In our earlier example, when we talk about the easy prime fields, so what is a prime field? Prime field is we can pretty much regard all prime fields as the set of integers mod some prime number, mod p, right? So this is field. If this is prime, if p is prime, then every element will have a multiplicative inverse, because we can apply Euclid's algorithm and extended Euclidean algorithm to find its inverse, as long as this is prime. Right? Now, the similar calculations can be carried over. The thing is, we have to have a concept of kind of like a prime polynomial. So if we can extend the idea of primes to the set of polynomials, then we can pretty much copy the same thing, and then construct a field. So this ZP is a prime field. How to construct this field? It's just ordinary integer arithmetic mod p. That's the only thing. If p is prime, then we can find its inverse. 好，所以前面讲的那个 field， 比方说刚刚讲的 field Z7， 对不对 ？Z7 有 F7， 怎么来的？它只不过就是最基本的整数的运算，你最后多加一个 mod 7的动作嘛，对不对？那这个 mod 7的动作，7是很关键，因为7是质数，所以7是质数的话呢，我们就可以 就用这个辗转相除，对不对？你最后就得到1嘛，得到1之后，你又可以迭代，我们所谓 backward substitution， 迭代，你就可以找到它的 inverse。这些动作全部可以搬过来。那现在就是说呢，你把它搬到这个，把它全部动作全部搬到多项式，其实全部都一样，唯一的差别是什么？你要有一个质数的概念啊，就是说你的多项式有没有质数概念？有的啊，多项式是有的，所以只要多项式有质数，我们就把原本的概念全部搬过来，全部抄过来就好了。So this can make sense if we can extend the idea of prime numbers to the set of polynomials. Okay, so if we can find a generalized idea of primes, then we can construct a field. We do not call those prime polynomials. We don't call them prime polynomials. We have another name called irreducible polynomials. Okay? So a polynomial is irreducible if we cannot factorize anymore. Okay? So it has no divisors other than itself. And then this concept is really important because it depends on, this concept actually depends on the ground field we're talking about. Let's take a look. So, for example, a polynomial is irreducible. For example, if like this, x squared plus 1. If we're looking at integers, ordinary integers, this is irreducible. This is irreducible in, for example, Rx. If we look at real numbers, it's irreducible. But it's not irreducible in Cx, right? And then it's irreducible in Zx. But it's not irreducible in Z2x or F2x. So this is irreducible. This is not irreducible. This is not. So it all depends on the underlying mathematical structure. It depends on this field or this ring, I should say. So it's not irreducible in Cx because in Cx you can factorize it as x plus this, x minus this, right? So this is in Cx, and then in F2x you can think of it as it can be factorized as this because in F2x this is equal to x squared plus 2x plus 1, but 2x is 0. There's no 2, right? This is XOR, so this is 0. 所以你同样的 x 平方加1，你把你这个系数是把它当实数，还是把它当负数，还是把它当整数，还是把它当 GF2， 就影响到你是不是 irreducible。那实际上你把它当做不同的这些哈，你同样这些东西里面都有1嘛，都有。但是同样的 polynomial， 你在不同的这个集合里面讨论，它完全是不一样的东西。除了它看起来一样之外，它没有任何其他东西是一样的，没有任何一点一样，就是根本是不同的东西。因为这个它的规则完全不一样，这样子的意思。So actually the idea of irreducibility depends on the set and the underlying mathematical structure of the set. So we can extend this idea. It's irreducible if it does not have any other factor. Okay. So if Px is irreducible, then Rx quotient Px is the field. Okay. So when we go up here, up to this point, it's getting a little abstract because we really don't know. We really can't. I should say, you have to imagine this thing because this thing does not have this thing is purely abstract. You can say it does not exist in the world. Okay, so it's a set of rules that you can't see. But this thing, even though you can't see, it's really important. So everything will be clear if you guys understand one example. Let me show you guys this example, and then after that, everybody will know. Okay. 好，我们看一个例子就好，我就看一个例子，因为我讲到这边应该蛮抽象的，对不对？讲这应该蛮抽象的，应该没有同学知道我的这个东西到底是什么，对不对？好，没关系，这个都正常。我只讲一个例子，你只要把这个例子看懂了，大家就会懂了。只有一个例子哦，大家集中精神把一个例子看懂。这个例子呢，就是 so this example, so let's focus on one example. If you guys can understand what's going on, if you guys can understand what's going on, then everything is clear. Okay, so let's take a look at f2x. This should be okay. This should be okay. So this is a polynomial in which all coefficients are in f2. So only x, or, and n. Now, let's find an irreducible polynomial. So I would choose the easiest one. Let's say this one, x squared plus x plus 1. So this is an irreducible polynomial. Yeah, this is irreducible. How do we know it is irreducible or not? Okay, because we only have very limited number of polynomials, so it will be very clear. So let's take a look. Okay, so x squared plus x plus 1. So let's say if it's not irreducible, then this is degree 2, right? They must be factorized as something, right? Two linear polynomials. 好，现在是 x 平方加 x 加1嘛，对不对？那我说它是 irreducible， 为什么？因为呢，你这二次的嘛，对不对？如果你可以再去继续分解的话，那是不是分解成两个一次的？那一次的 polynomial 是什么？就是一定线性的嘛，那你就是两个系数，一个线性的系数，一个常数，对，一定是什么 x 加什么？来，我们来看一下，什么 x 加什么？什么 x 加什么？对，什么 x 加什么？ Okay, we can fill out these blanks. Fill out these blanks with only zeros and ones. So we only have 4 possibilities. So these two, either 1 0 1 1, 0 0 0 1 1 0 1 1. So only 4 polynomials in linear terms. So we only have so 0 0 is just 0. Okay, and then we have 1, and then 1 0 is x, and then 1 1 is x plus 1. So only 4 polynomials. We don't have to consider this because this is not a linear polynomial. So only this one, okay? So only 2 possible polynomials of degree 1. So 2 polynomials multiply together, and there are only 2 possibilities here. 2 possibilities here. So only 4 possibilities. 总共只有4个 polynomial. 我们把它全部写出来看看。So only 4 polynomials. So this is either x or x plus 1. X or x plus 1. Okay. Let's see, x times x is equal to x squared. Obviously, it's not this. X times x plus 1. So we just write them. Okay. X times x is this. X times x plus 1 is x squared plus x. And then x plus 1 times x is the same. Right? X squared plus x. X plus 1 times x plus 1 is x plus 1. So they're not equal to this. Obviously, this is irreducible. Okay. 所以这4个乘来乘去，那都没有啊，都没有啊，它就不可分解 irreducible. 好 ，so this is irreducible. No big deal. Now let's construct this. Okay, so we are considering every polynomial mod this. Okay. So what do you mean by that? Okay. That means if you have any polynomial which has power which is degree 2 or more, then we can reduce its power because we can do long division. For example, 任何2次含以上的多项式，你都可以去除这个 x 平方加 x 加1。那它剩下的，请问除完之后，它余式是几次呢？就一次，这样的意思吗？只有一次。比方说 ，let's say whatever polynomial is right. For example, x cubed plus this plus x. Let's say you have a polynomial, right? You can do the long division of this, right? X plus x plus 1. Then you end up with, so this is x cubed plus, this is x squared plus x. And then we have x squared plus 0 plus 1. And then plus 1. And then we get x squared plus x plus 1. Finally, we get x. So in other words, what we have is x cubed plus x plus 1 is congruent to x plus 1. No, to x, congruent to x. So any polynomial has degree, any polynomial having degree 2 or more can be reduced to a linear polynomial according to this formula. So this is congruent to this. In other words, in our mathematical structure, we regard this polynomial and this polynomial as the same thing. 我们把这个 x 3次方加 x 加1就把它当成 x 而已。换句话说，你只要超过一次，就2次以上，全部把它一除下去，它余式绝对是一次。那一次只有4个 polynomial， 0 0 0 1 1 0 1 1嘛，就是0跟1 ，x 跟 x 加1。换句话说呢，这个 finite field 总共有4个 elements。So in other words, this finite field has only 4 elements. What are the 4 elements? So this is our finite field. This is called F4 or F4. Only has 4 elements. 0, 1, x, x plus 1. This forms the theory. So addition, subtraction is okay. Multiplication, let's see. So multiplication, we have a multiplication table. So we call this 0 and 1, right? So 0 is 0 and 1 is 1. So this is, we call this, we represent the 0 as 0, 0, and then this is 0, 1, 1, 0, 1. Okay, 4 elements. Let's look at its multiplication table. Okay? So we have 0, yeah, let's just use polynomials because that's easier to understand. X. So 0, there's no big deal. It's all 0. All 0. And the 1. Okay, and then x. X times x is x squared. Right? X squared. So this is x squared. Okay, what is x squared? We gotta do x squared mod x squared plus x plus 1. This is x squared mod this. So x squared mod this is actually, if you guys can do mental math, they actually, x squared and x squared, they cancel each other. So this is x plus 1. 大家可以心算吗？平方的话，你跟它平方消掉，剩下后面这2项就变成负的。可是没有负的，负就正，正就负，因为 F2， 这就剩下x加1。我们就如果同样可以心算，你心算一下，这是 x 加1哦，这一项 x 加1。x 乘以 x 加1是 x 平方加 x。x 平方加 x 再骂的，如果心算够厉害，就是1，哈哈。直接帮你心算，好，同学有兴趣自己算一下。So anyway, so this is this. So this is x. So this is x squared plus 1. So what is x squared plus 1? Because x squared is x plus 1. So that means x squared plus 1, right? X squared is x squared plus 1. Plus 1. Right? I'm sorry. X squared is x plus 1. Plus 1. So it's actually x. This is x. So every element has its multiplicative inverse. So 1, okay? 1's multiplicative inverse is itself. X and x plus 1 are multiplicative inverse of each other. So these two are multiplicative inverse. So everything has multiplicative inverse. So you have 4 elements, right? 0, 1, and 2. And then when we talk about multiplicative inverses, we don't have to look at 0. So this is the multiplicative inverse of itself. They are the multiplicative inverses of each other. It's which becomes a field. 好，最简单的说法，同学们只要把这个例子看懂，就懂。因为今天同学们，假如几年后你毕业了，然后你已经忘记这什么了，对不对？你只要知道什么叫做 GF4 就好了。因为 GF4 它没有办法用不抽象的方法表示，它就是一套规则。那这套规则有没有办法应用在自然界的这个事情上呢？有没有自然界东西这个呢？好像没有。它纯粹是一套游戏规则，要用完全抽象。但是它呢，它这一套规则全部符合 field 的每一条。你有乘法、反元素，有乘法，对，你有加法、乘法，减法跟加法一样。所以这一套规则就可以应用在 error correcting code 上面，而且它刚好只有0跟1，它可以很简单的用那个 binary 的方式去表示。只不过这套方法没有办法用抽象的，没有办法用不抽象，用具体方法表示没办法，因为你不用 polynomial 没有办法把这个东西给表示出来，必须要走 polynomial 才会。走 polynomial 就牵涉到它的规则，对，直接牵涉到它的规则。但因为它 element 很少，你就算是不用这些规则去算，我直接硬性规定你，好，我就硬性规定0001101110乘以10等于11。你如果直接这样规定的话也可以，只是说这样的规定，那你要去符合，它是不是有结合律啊？它有没有交换律？你硬性规定当然可以啊，对不对？那你要去一条一条去验证。那实际上我们因为这个表不是硬性规定来的，是透过 polynomial 绕一个弯得来，所以它因为透过 polynomial 关系，它就继承了 polynomial 的那个交换律、结合律的东西，本身它就继承。那它实际上从那些规则，它就变成这样的东西。所以这个东西它抽象在哪里呢？它抽象在哪里呢？他的问题就是说，你要表示一个 GF4， 你没有办法绕开这个 x，x 是什么？什么是 x 呢？这就是一个问题。等一下，我跟教同学另外一种观点去讲什么叫 x 啊，因为你绕不开这个 x 是什么？它是多项式，什么是多项式 ？x 有含义吗？有含义，但是你没有办法用个具体的东西去表示它。那等一会儿呢，我用另外一种观点帮同学们解释一下。让同学可以解释这比较理解这抽象的东西。到目前为止有没有问题啊 ？So that's the way we that's GF4. It's abstract. It's purely abstract. But I will find a better way to get around the idea of x because there is no clear definition of what x is. In AES, which we're going to teach later, it's not just GF4, it's GF256. And then they have another irreducible polynomial, not this one. So the polynomial, that irreducible polynomial is of degree 8. Okay? So those things are purely abstract. But I mean the ideas are the same. Later I will find a better explanation. Okay, so let's move on. We can extend the Euclid's algorithm on polynomials. So the GCD, fx and gx, those are polynomials. We can extend those to find the greatest common divisor. Okay? And the finite field construction to construct gf to the power of p to the power of n. First, we have to find an irreducible polynomial of degree n. Okay? And then we consider ZP, which is the polynomial ring mod p is prime, integer. mod another polynomial. That's GFP to the power of n. 好，所以什么叫 GFP 呢 ？PTN 首先你要有 GFP。好，什么叫 GFP 呢？就是它是整数，它这个是数字哦，mod p 这些东西是多项式的系数的规则。当时系数的规则是 mod p， 然后呢，多项式本身的规则呢是 mod p 的 x。那你要找一个它的 degree 是这个n 次方的这个有点说回到。不过我们不用担心这个问题，因为实际上在用的时候，你可以直接查表，因为都会有所谓的这个 irreducible polynomial table， 就直接查表就好。对，实际上呢，因为大家都已经算好，因为实际上怎么找 irreducible polynomial 是一个很大的问题。对，因为我并没有跟你讲怎么找，我刚刚在这边怎么找的？暴力法，因为法上 GFP 很小，它这个才 GF4， 对，太小了，只有4个 polynomial 当然没问题。但是实际上，比方卫星通讯用到 GF 不要多少，1024、2048、4096都有，8192都有。那你8000多的话，你要找个要找一个 degree 8000 ，degree 是吧？8192是2的13次方你要找一个13次的一个 irreducible polynomial 就没有那么好算，因为你有8000多个东西要让你算，那就不是说列表就列得出来了。你8000多个你列表不列，没办法列。光是你 AES 256个就很难算啦，那个都要用就是直接查表。Okay, so anyway, so that's the idea. Now let me give you guys another way of let's think of it as another way. Okay. Now, when we do mod this, there's an alternative point of view. The thing is, anything that is a multiple of this x squared plus x plus 1 is regarded as 0. For example, obviously, when you have x squared plus x plus 1 times anything, gx, right, will be regarded as 0. 什么叫同余呢？就它的倍数把它当成0的意思，对不对？它的倍数当成0，就是说你把它当成0了，知道意思吗？就这样就可以。So in other words, this irreducible polynomial will be regarded as 0. In other words, this is regarded as 0. So it's if we look at this from a different point of view, it actually means we can have addition, subtraction, multiplication, and then we introduce a new relation. What's this? Which is an equation of degree 2. Okay? So let's say if there is a solution, just think of an imaginary solution. So what is it? So let's say we have an imaginary solution alpha. Alpha. 好，我们现在把这个东西当成0嘛，对不对？我们把 x 平方加上 x 加1当成0，然后我们把它当成一个2次方程式。但是2次方程式不是在整数里面，在什么呢 ？F2 里面。那这个方程式在 F2 里面是无解的，这样知道意思吗？你比方说你的 F2， 你把 x， 你用 x 用0或1代进去，它永远不可能等于0，这样知道意思吗？ So this equation does not have any solution in F2. Yeah, for example, you put 0 there. You put 0 there, they disappear, and then it will be equal to 1. If you put 1 there, then 1 plus 1 plus 1, it's still 1. Okay, so in other words, this equation does not have a solution in F2. Well, it does not have a solution. That is okay. Let's think we have an imaginary solution called alpha. Okay, so if we have an imaginary solution alpha, then this F4 can be regarded as this. So this finite field GX4 has 4 elements. 0, 1, and then the imaginary solution alpha of this equation. And then alpha plus 1. 好，这个时候 F4 我们就不把它当多项式，我们把它当成什么呢？你现在这个东西是一个无解的方程式，然后我们想象它有一个解，好，那把这个解放进去，然后呢，阿尔法跟阿尔法加一，好，那么这个 x 我们把它改成阿尔法，阿尔法跟阿尔法加一，那实际上 x 就是阿尔法嘛，你可以这么想，但是这时候阿尔法呢是有意义的，因为阿尔法是一个虚构的根，那这边就变成阿尔法啦，你看阿尔法，好，那这些都变阿尔法，但是你阿尔法呢？满足这些条件，你阿尔法是虚构的，可是阿尔法有阿尔法呢？我们知道阿尔法平方加阿尔法加1会等于0，就这个意思。就是你这阿尔法会满足这个方程式。这个是你在做这干嘛？有点在像做什么？做那个 complex numbers 一样，复数，虚数嘛。这个就是一个很抽象的一步。当初数学家觉得，你为什么要虚数？你明明 x 平方加1没有解啊，对吧？我们现在做的事跟虚数是一样 ，so that actually what we are doing right now is exactly the same thing as constructing the complex numbers from real numbers. So from real numbers, we end up with a irreducible polynomial. This is an irreducible polynomial in Rx. This is irreducible. So in other words, this equation does not have a solution in R. Okay, it does not have a solution, but that's okay. Let's think it has an imaginary solution. Let's imagine it has a solution called I. 所以我们把它想象这边它有一个解叫 I 嘛，那 I 是什么意思 ？I 的平方加1等于0啊 ，I 就根号负1的意思啊。它本来没有啊，那你先把你想象它有。想象它有，那你什么叫复数 ？So what is a complex number? The complex number is nothing more than a plus bi. That's exactly the same thing we're doing right now. It's the only difference is this imaginary solution alpha is not a complex. It's not the imaginary solution of x squared plus 1 in Rx. It's actually the imaginary solution of x squared plus x plus 1 in F2x. That's the only difference. 好，所以这边的虚根是 x 平方加 x 加1在 F2x 里面的解。复数的虚根是 x 平方加1在实数里面的解。就这个意思。所以你只要跨过这一步，这一步有点难跨，你知道为什么很难？因为当初数学家说，你明明没有根，你干嘛想要它有一个虚根？这是虚构的，所以很多数学家是觉得说这个东西没有用，它明明没有，你干嘛要用？但是有一些其他的数学家，就包含了高斯啊、高斯基，他们认为说呢，他就跨过这一步，就是说我先不知道它们有什么用嘛，对不对？没关系，就先跨这一步，我们就先想象它，然后单去算算看吧。后来发现它真的有用。同样的概念，如果同学们能够跨过这一步的话，那你就跨过去了。对啊，因为它是完全是一样，就在代数上一模一样，差异只在于你讨论的 field 不一样。这边讨论 field 是 F2， 那边讨论的 field 是实数是 R。这边讨论的 irreducible polynomial 是 x 平方加 x 加1，那边讨论的是 x 平方加1，差在这里，其他一模一样。那这样就可以把原本的 field 扩展。所以换句话说呢，虚数里面呢，我们可以看到什么叫虚数？原本你的实数就一维的，我们把它看成一个 vector space， 一维的变两维，就是说你这边的 vector space 这边是 R， 对不对？这边有一个 basis 的 vector 是1，这是一个 basis。那还有另外一个 basis vector 是什么？根号负1。然后呢，那你由这个1跟根号负1所 span 出来的那个的 vector space， 两维的 vector space 就是 complex numbers， 这边一样。就你这边的根有一个叫阿尔法， 有一维是阿尔法的，另外一维是一，那 span 出来的两维哦，这是两维的向量空间哦，但是它是有限的，它一维只有两个东西，每一维只有0和1，它是两个维度，这样子就变成什么？这个就是 GF。好 ，Okay, so that's the idea. Now let's take a look at another example. That will be even clearer. So let's take a look at this. Example of GF8. Let's use the first way of description. We find an irreducible polynomial, which is this. This is another big topic, but let's don't worry about it now. I'm telling you, this is irreducible. So we have a px, okay, and then what is GF8? It's z2x mod px. So then, and then we can limit this power of every polynomial to up to degree 2. So we only have 8 polynomials. Okay? So we can regard these bit strings as polynomials. And then we do these operations. And then let's take a look at the multiplication table. So at addition tables, there's no big deal. So we have 8 elements, right? 0, 1, x plus 1, x plus 1, x squared plus 1, x squared plus x, x squared plus x plus 1. Okay? And then we can use these numbers to represent it. That's exactly what it is, right? So this is GF8, and then we can have the multiplication table according to this. Okay? Let's switch to another view here. So what is GF8? What is GF8? So here it should be very clear that GF8 is, first we have to have an irreducible polynomial. This irreducible polynomial is x squared plus x plus 1. So this is irreducible polynomial. And then we regard alpha as an imaginary root to this polynomial. Okay, alpha is an imaginary root. Okay, let's call this px of px. Okay. Now we have 3 dimensions. Okay, 3 dimensions. We consider the vector space spanned by 3 basis vectors. We have 1 dimension, which is 1, and then this dimension is alpha, and then this dimension is alpha squared. So 3 dimensions. And then this dimension, it's only 0 or 1. 0 or 1, and this dimension 0 or 1. This dimension 0 or 1. So altogether, there are 8 elements. That's exactly the same. And then we have a relation that alpha cube plus alpha plus 1 is 0. So we can calculate all those things. And then this GFA can be pretty much represented as 0, 1, alpha plus 1, okay, alpha square plus alpha square plus 1, alpha square plus alpha plus alpha square. So 8 elements. 就总共8个。这就 GF8， 是 GF8 变成3维，居然16变4维。那我们用到 AES GF2，GF256就有8维。Okay, so let's stop here. We'll continue next week.